Okay. Revision again. We know vector space, vector subspace. You need to know these notions at least intuitively, and if you forgot the exact criteria, you can check it. Complex conjugates, ket, bracket, complex conjugate, transpose complex conjugate, which is dagger, Hermitian conjugate, or adjoint. Dagger is Hermitian conjugate or adjoint. Basis, the fundamental theorem of linear algebra. Span, linear independence, the criteria for these, like rank of a matrix and this kind of things. How to calculate the rank, you need to know some linear algebra, this kind of things. Linear operators, you have two vector spaces or subspaces. And you have a linear operator A, works such as in the way that you have a linear combination of vectors from the first spaces. It acts on these and it's going to map it to, let's say, something like this. Goes in. Then for a linear operator, we have matrix representation of that linear operator, which is different toward different bases. You have A acting on a linear operator. Well, the vectors of the first vectors of the first basis vectors of the basis of the first vector subspace or space, whatever. So Vi, these are the vectors of the basis of this, of V. It's gonna be W, not W, A, Ij, W. So I think this is going to be I, J, J. Hilbert space is exactly the same thing as the inner product space in a finite dimensional complex vector spaces that accompany quantum computation. There's a definition of a dual vector is just ket. Sorry, bro. Dual vector, not a name for bro or something, whatever. Inner products definition. It has three criteria, and basically you can check it. We have norm of a, what's this? And if psi is, then the norm is normalized for the qubit. For a, let's say x1, x2, xn forms the basis for W vector space, and it's not orthogonal and they're not normalized. So if there's a technique called Gram-Schmidt's technique, you can just put in Mathematica or MATLAB or ChatGPT or just do it by hand, and you're gonna end up having x1 prime, x2 prime, xn prime. Okay. Such that xi, xj for I not equal to j is equal to 0, and for I equal to j is going to be equal to 1. The Cauchy-Schwarz inequality is a geometric fact about Hilbert spaces, inner product space, finite dimensional inner product space within QIP. For any two vectors, you have the inner product of a vector with itself is not necessarily 1 as long as it's not normalized. So you can bring in a completeness relation, which is I over, like, we can do this, V, I, V, and I is V. What are I's? This completeness relation, and also we heard about something called diagonal representation. An operator is it's called diagonalizable, and I think is diagonalizable. It's not thinking, it is. This is a proof. With eigenvalues, equivalent, degenerate eigenvalues 1, 1, 1, 1, 1, whatever. So this comes out I, V, I, V. And these are the basis of any V and W are just two any vectors from the, let's say, vector space X, whatever, I didn't care. And I's goes through all of the vectors of this basis. So one of these, because they are one of these, they are not necessarily orthonormal or orthogonal. One of these is definitely here. So this is, because this is sum, right? And because this is inner product, an inner product of two vectors is always positive, greater or equal than 0. So this is going to be equal or less than this. I need to write it better. V there you go. So this was this. I went the other way, so I made a mistake in the proof. I's, they are of normal basis using Gram-Schmidt process on vector space X. First member is yeah, it makes sense right now. So this is equal to, I just made a mistake here, typo. So this comes out I gonna be equal to the first one. This is the sum, right? And these are inner products. So equal to the first one, we choose the first one, which is this goes with this, and this is going to be equal to V. So the inner product of two, this is bigger than equal to V. Eigenvalue and eigenvector. We have A and as an operator works on this, and A comes from here, lambda. It's an operator, right? Okay. And there's something called characteristic function. Characteristic function. And characteristic equation. Function is C lambda, and this is equation, and this is the function. The determinant of A minus lambda I equal to 0. And the way to find the vector eigenvectors is and this is on vector space V, from V to V. Doesn't change. The eigenspace corresponding to an eigenvalue is the set of vectors which has eigenvalue V. If eigenvalue V has more than one eigenvector, it's called degenerate. And there's a condition that we're going to learn later for diagonalization, or being an operator being diagonalizable. And if it's diagonalizable, it's going to be like this. And this is of normal basis. Of a normal set of eigenvectors. So we're gonna do 2 questions and we're done here. Second one is 1, 1, 1, 0. Not diagonalized. Not diagonalizable. I is 1 plus 1 0 0 plus 1 1 1. X is plus 1 plus minus 1 Z is and Y is plus 1 I. It was not I. Yeah, it was I. Plus I minus 1 minus I. And plus I is 0 plus I, and minus I is that's it. Not diagonalizable. First characteristic function is going to be a minus lambda I, determinant equal to 0. So it's going to be 1 0 1 1 minus lambda 0 lambda 0. So it's 1 minus lambda 0 1 1 minus lambda. This is going to be lambda is plus or minus 1. Now we go to the vector, the eigenvectors. It's 1 0 1 1 minus lambda I. Let's say lambda is 0, is plus 1, and it's going to be alpha beta. So this is going to be equal to 1 minus 1 1 minus 1 0 1 1 minus 1 alpha beta. This is going to be called 0 0 1 0 alpha beta 0 0. So this is 0 and this is alpha 0 0. So alpha is 0. So lambda equal to 1, alpha is 0, and for being diagonalizable, it's for normal set. So this doesn't need to be normalized. So alpha to the 2 plus beta to the 2 is. Wait, let me check. Let's not rush. And we got alpha equal to 0 for this. And how would this one? Lambda equal to minus 1. It's 1 0 1 1 minus minus 1, 1, 0, 0, 1. So we're gonna add this plus. It's 2, 0, 1, 2. Alpha is 0 plus beta. So this is 0 and this, so beta is 0 too. So eigenvector shouldn't be 0. So we don't have an eigenvector. So when we don't have an eigenvector, it's not diagonalizable. Simple as that. Get a life.